Okay, good afternoon, everyone. Let's get started. I wish everyone has enjoyed your spring break. And but just reminder, our homework 2 will be due on this Friday. So if you haven't started, please do it right now. Right. The number of problems is not big, but you still need some time. And if you want to seek for help, please leverage our office hours. Okay. So let us continue with the inference problem in graphic models. Right? At the last lecture, we introduced this so-called sum product algorithm framework. Sorry. So we discussed previously, if your graphic model is a tree means that there's not any loop in the graph, right? So then you run some product algorithm, it guarantees to find out the exact marginal distribution for every variable node in the graphic model, right? And why is this true? It is because the sum product algorithm is in essence based on the leverage of this distributive law when you couple the sum and product operations. Okay. So at the beginning, we use a chain graphic model as an example, right? We show that how we, if we first multiply all the factors in the joint probability together and then enumerate different combination of variable values and calculate the marginal distributions, this is really, really expensive, right? So to avoid that, we should apply a distributive law. That is, we try to aggregate or sum over the variables as much as possible before we multiply with others, right? We first do sum and then do the product, rather than do product first and then do the sum finally, right? So that is the distributive law, right? This is a simple example, shows that how powerful distributive law is, right? If we just multiply, if we first do the product of this A1, B1, A1, B2, A2, B1, A2, B2, and then do the summation, you'll find it will take 7 operations in total, right? However, if we first do the summation first, or more in general, aggregation first, we first aggregate A1, A2, and then aggregate B1, B2, and finally do the product, then you reduce number of operations to 7 or to 3, right? Reduce a lot. So the sum product algorithm uses exactly the same idea, right? It leverages the tree structure of the graphic model to do the summation as much as possible before we do the product. Right? That's the key idea. Right? The key idea is that, okay, I want to smartly leverage this law, right? I want to do the aggregation or do the sum as much as possible before I apply any product. Right? So now let us take a quick review of this sum product algorithm, right? I'm not gonna go through the detail again because I believe everyone has captured that detail. I just want to let everyone to pick up quickly one idea, right? So suppose we want to ask them, I want to compute the marginal distribution of one variable x, right? Here's x. And from the naive rule, we're gonna sum over all possible configurations of the random variables other than x on this joint distribution. Remember, this joint distribution essentially is the product of all the factors, right? And each factor is associated with a set of variables, right? So that means if you naively do this marginalization, that means you're gonna multiply all possible factors together. You do the product first, and then you do the summation, right? That is the most inefficient way, right? So how can we improve the efficiency, right? The key observation is that, okay, if we will x is the root of the whole tree, right? So for a tree, that means you can pick up any node in this graph as a root, and then you can form a tree. right? And because it's a factor graph, then all the neighboring node to X will be factors, right? So we can view each neighboring factor as a root of a subtree, right? So this factor will be a root of a smaller subtree. This factor will be root another smaller subtree. This factor f of s, fs will be root of a small subtree, right? Because this is a tree structure, it means all the factors and variable nodes inside each subtree are non-overlapping across different subtrees, right? Why? Yeah, because this is a tree, right? If there's overlapping, that means, okay, you can find another path which connects two nodes across different trees, then you kind of form a loop, right? That won't be a tree, right? So this non-overlapping properties across different subtrees give us an opportunity. That means when we do the aggregation over the variable nodes across different subtrees, we actually can do it subtree wise, right? So we can do the aggregation. Remember, because we want to do the marginalization over X, right? We have to marginalize out all the variables inside all the subtrees, right? Because all those variables across different subtrees are not overlapping. So that means we can do the aggregation inside each subtree in parallel. They are not influencing each other at all. Right? That's the key idea. So that means when we do this marginalization, right, we can first compute the aggregation result from each subtree rooted by a neighboring factor node to X, right? And then multiply them together. So you can see this is how we apply the distributive law, right? We first do the summation or aggregation inside one subtree, and then do the product, right? We move the summation in front of product. So we can expect to reduce some computational cost, right? So we define the aggregation result rooted by a particular factor node, Fs, neighboring to X, as a message sent from this factor to the variable node X, right? This comes out our first type of message, which is message from a factor to a variable node, right? So you know that, okay, if you want to compute the marginal distribution of a variable node X, right? We just need to compute the message sent from every neighboring factor of X to X, and then multiply them together, right? Okay, I mean, if you feel uncomfortable about that, just try to think about what we have discussed previously. But if you still feel uncomfortable, that's fine. I spend some time after the class and to think about what you have discussed. Right? But interrupt me if you feel if you want to discuss. Right? And then there's a question, right? If you want to compute this message, how do we do that? Right? If you want, for example, take a particular factor Fs as example, right? If you want to compute the message sent from Fs to X, how do we do that, right? As we mentioned, this message essentially is the aggregation results of all the variables and factors inside this subtree rooted by Fs, right? So that means we're gonna from the naive definition, we're gonna first multiply all the factors inside this subtree, right? Inside this subtree, and then marginalize out all the variables inside the subtree, right? That is the summation here, right? Here, right? So to efficiently compute this message, right? So we need to further look at the structure of this subtree. If we look at this factor Fs, right? Because Fs is factor, then all of its neighboring nodes are variable nodes. Okay? So now X, which is the target variable, which we want to compute the marginal distribution. X is a parent node of Fs, right? So all the other neighboring nodes of Fs will be its children nodes, right? So you see that every children node of Fs will serve as the root of even smaller subtree, right? Remember, the tree structure is kind of recursive, right? Each child of Fs now serves a root of an even smaller subtree. And even better, all those smaller subtrees are non-overlapping, right? So that means when we do the aggregation over the whole subtree rooted by Fs, we can first do the aggregation inside each smaller subtree rooted by each child of Fs, right? Following a similar kind of rule, right? And then we get these results, we multiply it together and multiply with this factor function Fs, right? That's the idea, right? Then we can define the aggregation results over each even smaller subtree rooted by a child node of the factor as the message defined from this variable node to the factor node, right? That's how we get the second type of message sent from a variable node to a factor node, right? And once we have computed the message from every variable node to the factor node, I mean the child variable node to the factor node, we multiply them all together, right? And then multiply with the factor function, right? And remember, eventually want to compute the message sent from the factor to its parent node, X, right? So that means we have to further marginalize out all the child variables of Fs, that is x1 to x big M, right? So we have found our rule to compute the first type message. That is, if you want to compute a message sent from a factor node to a variable node, we first compute all the messages sent from a child variable node of the factor to that factor, right? Multiply them together with the factor, and then marginalize out all the child nodes, all the children nodes of the factor. Does it make sense? It's very easy to memorize that. Everyone is comfortable? Okay. And then we come to the next question, right? We know how to compute the message sent from a factor node to a variable node. And this computation is based on the message sent from variable node to the factor node. And the problem is that how do we compute the variable node to the factor node, right? The message from variable node to the factor node, right? So again, we're gonna kind of like decompose the structure, right? Now, if we want to compute the message from a variable node xm to a factor node fs, now fs serves as the parent node of xm, right? And all the other neighboring nodes to xm will be its children node, right? Again, xm is a root of a subtree. Then all of its children nodes, every its children node will serve as the root node of even smaller subtree, right? And again, those smaller subtrees are non-overlapping, right? So that means we can again apply the distributive law. We can do all the aggregation inside each smaller subtree, and then multiply together to get to the message sent from xm to its parent fs, right? So that reduces to our rule to compute the message sent from a variable node to factor node. Okay, do that. We just compute the aggregation results of all the product of factors inside each smaller subtree. Each smaller subtree is rooted by a child factor node of xm, right? And then multiply them together. In other words, we first compute all the messages sent from its child factor to the variable node xm, then multiply them together. Okay. And then we have summarized the two rules, right, to compute two types of messages. Right? It's kind of like recursively and alternatively computation procedure. Right? We have two types of messages. One type of message is sent from a factor node to a variable node. The other type of message is sent from variable node to a factor node. Okay? And once you got a factor node, if you want to compute the message sent from fs to x, right? You need to look at all the other neighboring variable nodes of the factor fs, right? You need to compute, or you need to have already computed the messages from the remaining variable nodes to fs, right? And then you multiply all those incoming messages to fs with the factor function, and then marginalize out all the neighboring variables, right? Other than the target variable x. That's how we compute the message sent from a factor node to a variable node, right? And if you want to compute the message from variable node to a factor node, things become even easier. Okay. So if you want to compute the message sent from a variable node xm to the factor node fs, right? You need to have the messages from all of its neighboring factors other than fs ready, right? So you have to compute all the messages from other neighboring factors to xm, right? And then what we need to do is just multiply them all together. And I have explained why and how these two rules are derived, right? So any questions so far? Are we on the same page? Any doubt and uncomfortable feeling about this? Or is it really trivial? Okay, yeah, hopefully, yeah. But again, in case you feel still uncomfortable about that, think about how you're gonna apply the distributive law, right? So this name, sum product, is nothing fancy. Just tell you, okay, this algorithm leverages two coupled operations, sum and product, and I'm gonna use distributive law to reduce the operations in this coupling of sum product operations. Okay. So let us continue, right? So you can see that these two types of messages, their computation are depending on each other, right? So there must be some initial or boundary conditions which can allow you to start the computation. And now this also requires us to define a computation order, right? As we mentioned, if you want to compute the message sent from a factor, arbitrary factor to arbitrary variable node, we must have all the other neighboring nodes whose message sent to this factor already, right? And also, if you want to compute a message sent from arbitrary variable node to a factor, you must also have all the other neighboring factors message ready, right? You must define a right order, right? When you compute something, you need to ensure all the required messages are done. Otherwise, you cannot conduct computation. So our next step will is to address this problem, right? So first, we need to consider what is the initial messages, right? So the initial messages are defined on leaves, right? So if your leaf node is a variable node, right? So that means F factor is parent node, right? And also it only has one neighboring node. That means there won't be any other neighboring factor nodes, right? There won't be that, right? And then we will compute the message sent from this variable node to F. Its message is simply 1. And the other situation is that, okay, suppose X is a parent and F is a leaf node. So that means F is only a factor function of one variable X. X does not connect to any other nodes. Right? There are not any other variable nodes that are connecting to F. Right? And when F serves as leaf node, then the message sent from F to X is simply the factor function itself, fx. Does it make sense? Okay. And then this addresses the problem that what if I got, for example, I want to compute something like this, right? Like this is a leaf node, right? If I want to compute the message sent from this factor F to this variable node X, right? So I need a message sent from here and sent from here, okay? Because this variable node and this variable node, they're leaf nodes. They have only one parent. They do not have any children. Then this message simply just 1. Okay? And similar base cases you can find it when F serves as the leaf nodes. Okay. And then the next thing is that how do we come out an order to compute all the messages? Okay? We need to ensure that at every step when we compute one message, all the required messages are ready. Okay? So here we introduce a type of message passing order. Right? It's called collective and distribution method. Right? How can we do that? Right. So first, we're going to pick up arbitrary variable node as the root. Right. So as we mentioned, right, given a tree, you can use any node to form the tree root. Right. And then according to the tree root, you can form the tree structure. Right. So you can pick up any variable node as the root. Right. Then you're going to do a message passing from bottom to up, meaning from all the leaves to the root, and then from top to the bottom. That means from the root back to all the leaves. Specifically, we first compute and propagate messages from the leaf nodes to the root and store the received messages at every node. Okay. And then we compute and propagate messages from the root to leaf nodes and storing the messages at every node. So if you conduct your sum product algorithm or the two types of rules, the rules to compute two types of messages in this way, from leaf nodes all the way up to the root node, and then from root node distribute back to every leaf nodes, then it guarantees that at every step, whatever message you're computing, the required or dependent messages have already been there. You don't need to worry about that. Okay, they're not ready yet. So this can be formally proved, but I will give you just some kind of idea of why this is true. Right? So give you an example, right? Suppose I want to compute the message from this variable node to its parent node, its vector node, right? So that means, I'm talking about from bottom to up, right? In the bottom to up procedure, in this step, right? Every time I just need to compute a message from a current node to its parent node, right? Then that will requires all of the messages sent from its child node to the current node, right? But from the previous procedure, because this is bottom to up, right? This is bottom to up. Once you move up to this node, that means all the messages from the children node to the current node have already been computed. That means they must be ready there. Otherwise, you cannot move up to this node. So because they're ready, so you can immediately use them to compute the message sent to its parent vector node. Does it make sense? So this is like an induction method, right? At the beginning, you can start from the leaf node. Of course, the leaf node, there won't be some incoming message from its children, right? It is initial message. It is either 1 or some factor message, right? And from here, you can immediately compute the message sent to its parent, right? And then that means at beginning case, your induction assumption holds, right? And then you can make assumption that, okay, at every subtree level, right? At every step, all the messages sent from its children to the subtree root has been ready, right? And then when you compute the message sent from the subtree root to its parent node, we'll be able to compute it because all the dependent messages there. Does it make sense? Right? It's very straightforward induction approach. Right? So once you get all the message from bottom to up, that means you have the messages computed from every node to its parent node. Right? Now you kind of distribute message, right? You can do this top to the bottom order, right? So let's see why this is correct, right? So if you want to compute the message sent from any, let me use another color, parent node to the children node, to the child node, right? What do you require? Right? So in step 2, right? I mean, we do this bottom up. We actually computed all the messages from every node to its parent node, right? And in third step, we essentially compute the message from every node to its child node, right? This top to the bottom, right? So if we compute any message, right, from a node to its child node, right, what do we need? Yes, exactly, right? So it needs this node is parent itself, right? This node is parent to this node first, right? And also it needs this node other child to this node message, right? You need to hybrid the message from the parents and also the message from siblings to compute the message to another sibling, right? The good thing is that if you do this, do these things from top to the bottom, we can assume that, okay, this message has been done in the previous step, right? It must be ready. So now that you got the message from your own parent, and you got the message from your other sons, your other children, right? You have everything ready to compute the message to the target children, or the target child. Does it make sense? right? Again, the rigorous proof can be done by induction, right? You can start with the root node, and it guarantees you that the root node, the message sent from root node to any of its child can be computed directly, right? And then you just apply the induction step and you can show this. Any question? There. Yeah, marginal every node. Can you see it again? Yeah, you're right. You're right. Yeah, that's a good observation. Yeah, exactly. But usually, because the computational cost of doing step 2 and 3 is the same. It's just linear in the size of tree. Right? If you are able to compute step 2, you are also able to compute step 3. And once you got all those, you are ready to retrieve the margin of every node. So people will usually do 2 and 3 jointly. Initial. Same condition. Yeah, we will use that example to illustrate in a minute. Any other question? Okay, great. So after the message passing is done, right? How to compute the marginals? We actually discussed this before, right? We can just pick up arbitrary node for which you want to compute a marginal. You just multiply all the messages sent from its neighboring factors to itself. That's it. Right? Right? Sometimes, as we mentioned, right? Sometimes if your graphic model is not normalized, right? You only know the product of the factors. It's not necessarily normalized. That means this product will simply correspond to an unnormalized marginal. Then you just normalize it. You get the normalized valid distribution. And this is important because in many practical cases, maybe your factors, the product of factors defines a valid drawn probability, but you know some variables are observed, like your data, right? You want to compute the conditional distributions, right? Y1 to yn, right? So in this case, you can view that, okay, those observed variables, they actually only take one possible value, right? Or their corresponding factor value only takes one possible value regarding that X setting, that variable setting. So then, if you want to compute the marginal distribution of any latent variable, you have to do the normalization as well. Okay. So some nodes have been observed. In this case, what we want to do is actually compute the posterior distribution, given that observed variables. This is very common when you do the Bayesian inference, right? You have a graphic model, you know some data are the observed variables, right? Then how do we compute the posterior distribution of the latent variables of interest? We actually fix the value of observed nodes in the message computation, and then when we do this product of the incoming message for any node, we actually get a normalized posterior marginal, right? And then you do the normalization, you get the correct posterior. Okay, so when we compute the message, right? Like let's use this rule as an example, right? So you can see that when you compute a message sent from fs to some variable x, right? So suppose one of your variable, see, let us take like x1 as some observer variable, right? So that means you might have a observe x, x1 c equals to 3. Okay. So then when you compute the message, you won't be able to take the summation over x1. You have to fix x1 to be 3. That means that applies to every variable which are observed in your graphing model. That's a very good question. Any other question? Okay. So next, we're going to use a concrete example to showcase how this algorithm works, right? So we're going to use a simple graphical model. We have 4 random variables, x1 to x4, 3 factors, fa, fb, and fc. From the definition of the factor graph, our joint probability is defined as the product of these factors, right? fa, x1, x2, fb, x2, x3, fc, x2, and x4, right? So how do we run that? First step, we'll pick up arbitrary variable node as a root to form the tree, right? So here we will use x3 as the root node, right? The whole tree root, right? So in the first pass, we're gonna start with the leaf node, right? Want to compute the messages one by one all the way up to the root node, right? Let us do this one by one, right? So first, we know that there are 2 leaf nodes, x1 and x4, right? So we first compute the message sent from x1 to fa, right? This is the initial, this is the boundary case, right? So its message, according to the rule we discussed, is simply 1. x1 to fa, x1 is simply 1, right? Okay. And then we compute the message sent from fa to x2, right? Here. Okay. How do we compute that? We just apply the rule we just summarized, right? So it's a message sent from factor node to the variable node. The way of doing this is to multiply the message sent from the other neighboring node to fa, which is x1, multiplying with the factor fa, and then marginalize out x1, right? This gives us the formula here, right? Because the message sent from x1 to fa is simply 1, right? You multiply 1 with fa, just fa itself, then you marginalize out x1, right? Then you compute the message, you got a message sent from fa to x2, right? Okay. And then let us look at the other branch, right? The message sent from x4 to fc, this is the initial message, is also 1, right? And similarly, when you compute the message sent from fc to x2, again, you multiply the message sent from x4 to fc, which is 1, with the factor fc, then you marginalize out its child, fc's child node, x4, right? You get the message sent from fc to x2, right? And then we got all the messages sent from x2's children node to x2, right? So see here we can see how our previous induction step in our mind holds, right? So we see that when we compute the message sent from every node to its parent node, all of its children's node, the message sent from children's node to its current node have already been ready. So that's why we can send the message all the way up. Okay, so we know the message sent from fa to x2 and fc to x2. With them, we can compute the message sent from x2 to fb. And this message essentially is a message from variable node to factor node. So the rule is very simple. You just multiply the message sent from its children, right? So it's a message fa to x2 multiplying with message fc to x2. Okay. And then we compute the message sent from FB to X3, right? And again, apply the rule. This is the message sent of FB to our root node X3. You just multiply the factor FB with the message sent from FB's child X2, and then marginalize out X2. So now you have finished the message passing from bottom to the top, right? So the next stage is to distribute message from top to the bottom, right? So and here, let me for clear, let me draw all the computed message with this green arrows, right? So when we propagate message from root back to all the leaves, right? We start from X3, right? So you can see that now when we compute X3 to its sole child FB, it becomes an initial condition again, right? So the message sent from X3 to FB to X3 is now become 1. That's our question. So and then we compute the message sent from X3's child FB to FB's child X2, right? Remember, FB only has one child X2, right? So to compute this message following the rule, we just need to multiply the factor FB with the message sent from the other neighboring nodes to FB, which is X3 to FB, which is simply 1, right? And then you marginalize out X3, right? So you got message sent from FB to X2, right? And then once X2 has received messages, it can further compute the message from X2 to its two children, FA and FC, right? The message sent from X2 to FA, you can see that if you want to compute this guy, right? We need the message from X2's parent to X2, which is this guy. And also the message sent from X2's the other children, FC, to X2. Okay? That's why we do need to first do the message from bottom to top. Okay? And then we do the message distribution from top to bottom. Right? So now we have both the message from the children and from the parent ready. We can use them to compute the message from X2 to its another children FA. Right? So this is done by just following the rule, which is simply multiplying the message sent from FB to X2 and the message sent from X2's another child FC to X2. Right? So that's where we get here, right? And then once you get the message sent from X2 to FA, you can further compute the message sent from FA to X1, which is just a straightforward application of the rule, right? And then similarly, you can compute the message sent from X2 to FC, and then FC to X4. And that's it. Right? Once you have arrived at all the leaf nodes in this tree, your message passing is done. Any questions so far? Okay. So if you're interested, you can try to look at, compute, and memorize all the messages together, and then multiply them together by using our rule, right? Remember when we compute the marginal distribution, we said that we can just multiply all the incoming messages from its neighboring nodes, right? We said it is the marginal distribution, right? You can try to look at the form of those messages, right? and multiply them together and say if it is really exactly the marginal distribution, and the truth is 8. Right? So here, give you some kind of justification, but I'll recommend you to manually confirm with this. Okay. Next, we're going to give some algorithm framework to implement this message passing framework. Right? So for convenience, we'll use recursive programming to implement this. That means we do not really try to, first enumerate who is the leaves and who is leaf the parents and so on, and do some kind of for loop over list of nodes. We're not doing that. Instead, in practice, it's always easy to do some recursive traversal programming over the tree. Okay. So can we do that? Right? So step 1, again, we're going to pick a root node X and arrange the graph into a tree. Right? You can imagine this is kind of your data structure course, right? You're asked to construct tree, right? Usually, if you use C++ or C programming, C language, you have to store some structure. You got some struct which store data, and also some pointer to point to the children, right? If my memory was not wrong, that's how I try to implement my tree traversal algorithm maybe 15 years ago or 20 years ago. No, actually, should be almost 20 years ago, right? If you use Python, it's kind of similar structure, but it's not some kind of pointer. It might be just some reference, right? Some reference to class instance, something like that. Right? So then in step 2, we're gonna start with the X, right? Start with the root node X. Okay. We're going to go through every child factor f of x. So that means we just do a for loop, go through every immediate child of x, right? And then we call this function collect f and x. And we'll go to the detail about this function definition later, right? But just be aware this is a recursive function, right? It will kind of recursively compute the messages from bottom to up. Right? It just tells that, okay, you're gonna collect the message all the way bottom to F, right? And then send the message from F to X. Right? And once you have done this, right? Once you finish this for loop, we're assuming that let me draw a better graph. Okay. Once you have finished this call, we're assuming that you have finished the message computation from all the way up to every factor f, and then you can compute the message from all the factors, child factor of x to x. That is, you finish the message passing from the leaves to the root node. Right? And then in step 3 is another for loop. We're going to go through the root node x children nodes again, children factors again, right? We're gonna call another recursive function called distribute. Right? This is still a recursive function. It just compute the message send from x to f, and then send the message all the way back to the leaf nodes. So that means once you have finished this loop, right? You have finished the message passing all the way down to the leaves. Right? So this is a whole framework. Does it make sense? Then let us look at how we design this recursive collect function, recursive distribute function. Right? So, this is a recursive collect function. Right? So it defines 2 types of collect. One is that you send a message, okay, from a factor node to a variable node x, right? So here, x means the parent node, and f is the child node. Right? And of course, there's another case that, okay, f is there's a factor node, and x is a variable node, it has a child node as a variable node. Like you still want to compute the message sent from this variable child to f. Right? That's why we define two versions of the collect function, and this can be simply implemented by the overloading property in modern programming language, right? So, first, when we talk about when you collect message sent from a factor node to a parent node or root node, which is variable node x, right? We need to consider okay. Oh, sorry. This is a so here, this is a case. Yeah. So this is a case. The collect xf is the case where you have a f. You have f factor node as the parent node and x as a variable node. Okay. And so fx is the case where you have the parent node as a variable node x and the factor node f as the child node, right? So we need to consider the corner case, right? So when we do this recursive programming, so first, if the child node x is a leaf node, that means it's not necessary to do any recursion, right? We should stop, and the message sent from child node x to f is simply 1. Right? This is how we define our initial message. Right? If it is not true, right? That means the child node x further has a bunch of child factor node, right? Right? Maybe f1 to f big M. Okay. So if you want to compute the message sent from x to f, what do we need? Yeah, we need the factor messages from x children to x first, right? That's why we need to call this collect function again, right? We need to first collect the message sent from is every child factor of x to x, right? All together, right? That's why it is gonna call this function, right? And then once you have done this, right? This is recursive call. Once you've done this, that means you have all the required or dependent messages are ready. Then your message from x to f essentially is just the message sent from, it's just the product of message sent from x children to x, right? Does it make sense? Okay. And then let us look at collect version 2, right? Which is about how do we compute the message from a factor node to a parent node, right? So here, we assume that, okay, the parent node is variable node, right? And the child node is factor node. Again, we need to consider the corner case first, right? The base case first, where if the factor f is a leaf, that means we have some initial message, and we should just return the factor function itself, fx, right? Otherwise, If f is not a leaf node, that means it has several variable children, right? Okay. Again, if you want to compute the message sent from f to x, we need to first collect the message from every f child to f. Okay, so that's why we have to run collect version 1 to get a message sent from a variable node to the factor node. And then once we have them ready, we can use our rule to compute the message sent from the factor f to the variable node x, which is multiplying all the messages from f's children with the factor function f, and then marginalize out f's children. Does it make sense? Okay. And similarly, we can design our distribute function, right? Starting from the root node and all the way back to the leaf nodes. And it follows very, very similar procedure as we discussed in the design of the collect function. So I will leave it as an exercise for you. Again, if you want to implement the sum product algorithm, this is the most it's the simplest and the most convenient way to implement that. Right? Of course, you can first you can use alternative implementation, like you can first do the tree traversal. You just remember the order of the nodes, and then you just go through list of the like store them in a list and just go through a list. You can do that as well, right? But doing this is always the simplest and the easiest way. So any questions so far? Okay. Yeah, as we emphasized, right? When the tree, when the graphic model is the tree, the sum product algorithm guarantee this is exact inference algorithm. All the marginal distributions are exact. Okay? But what if your graphic model is not a tree? What if your graphic model has cycles, right? Has loops? Can we still apply this algorithm? Don't be pathetic. Well, 25 years ago, people also asking about this, and before people figure out whether this is feasible, some practitioners just, okay, let me try this. Okay? Let me just blindly try this and see what happens. And the result is that it is applicable, and also the result is surprisingly good. Okay. So here is the conclusion, right? In general graph that contains cycles, sum product cannot guarantee exact inference. Right? However, you can still apply it as a proximate inference algorithm, and in practice, it often works pretty well. So before we talk about that approximation, right? So someone might ask, right? So is there any exact inference algorithm on general graphs? Right? The answer is yes. This type of algorithm is called junction tree algorithm. So the idea is quite straightforward. So the idea is to change the factors. So if we use your definition of factors, you have your own graphic model which contains annoying loops, cycles, right? So to avoid that, why not try to merge factors? Suppose I may define a factor fa, which is function of x1, x2, fb is function of x2, x3, right? If I can merge fa and b, I can get a new factor, right? I denote it by f tilde, which is function of 3 variables, x1, x2, x3, right? I can do that, right? if I can smartly merge those factors, and based on the merge factors, I can still construct a graph which is tree structure. So this tree is called junction tree. Right? So you can see that the K here is how do you smartly merge the factors and to form a tree structure. Okay? And the idea, I mean, the basic idea is really do some kind of triangulation and then try to merge them. And but the problem is that you want to merge those factors to form a tree structure, but also don't want your tree, the new factor, to be too large. Right? So, for example, my previous two factors are only functions 2 variables, right? If we merge them together, it now becomes a function of 3 variables. That's really bad, right? Because for factor A, I only consider combination of 2 variables, right? Factor B, I only need to consider combination of 2 variables. But for my new factor, I have to consider a combination of 3 variables, right? When I compute the message, remember the message, I'm marginalize out a bunch of variables inside the factor function, right? So if your factor function is too large, meaning you have too many input variables, the message computation itself is really, really expensive. Right? So when you do the junction tree, when you construct such a junction tree, you want your merged factors to be as small as possible. And the bad thing is that to find out the smallest setting of such merged factors, it is simply hard. So people always have to use some like greedy algorithm to construct such a junction tree. And also, even you can do that, you will see that your merged factors is often very large. Maybe it contains 5 variables or even 6 or 7 variables. Like consider each variable, it might have like 4 values, right? Or 5 values. Then the total number of possible combinations would be 4 to the power of 7, 4 to the power of 8. That means if you compute one message, you have to enumerate that many configurations. That is quite slow. Right? Even you can guarantee some kind of like exactness. That's why junction tree is kind of elegant in theory, but in practice, people rarely use that. Does it make sense? Just give you some kind of sense how this exact algorithm is working, right? But we don't need to know detail, right? In practice, people often prefer to just blindly apply the sum product algorithm for arbitrary graph, no matter it contains loops or not, right? And how can we do that, right? Because the tree is not guaranteed to be, the graph is not guaranteed to be a tree, right? That means it cannot order a tree structure and to decide an order of the message passing such that every time when you compute a message, all the dependent messages are ready. It's not applicable, right? So in practice, we just initialize all the messages with 1. And then when I do the message computation, I just assume that those messages are already there. I just pick up compute. An alternative will be, okay, I just do random initialization of those message values. And then I just run some product. And with any message passing order, I do it repeatedly until convergence. And usually if it converges, it can work really well. Right? But sometimes it might not converge. It might diverge. In this case, it usually means that your message passing failed. You need to rerun. Either you re-initialize those messages with another random values, or you change the order of your message passing. Like you run multiple times until convergence. Right? So this type of method is called a looping belief propagation, and it has a astonishing connection to the turbo codes. Right? So If you're from ECE, you will know the turbo codes. The invention of turbo codes is kind of revolutionized the coding theory, right? Because it's the first coding scheme that is so close to the channel limit, right? And the people find that the profound connection between the loopy belief propagation and turbo code, right? So, but here I just want to give you a little bit more introduction about why you run some product algorithm blindly. Sometimes it might not converge. The reason is that if you run some product right blindly or arbitrary graph, you can view it as an optimization problem. But this optimization is neither a maximization nor a minimization problem. Instead, it is a max-min problem. So your running of some product essentially is to use some kind of fixed point iteration to solve that kind of problem. So if you run fixed point iteration, usually it's not guaranteed to converge. Right? It is easy to diverge, especially when you update as compared to the previous step is too large. It's very easy to diverge. Okay, and there's a more general version of this loopy belief propagation, which is called expectation propagation, which applies to continuous value random variables and message passing on that. Okay, so any questions so far? Okay, the remaining thing we want to discuss is a variant of sum product algorithm, which is also very, very useful. It's called a max sum algorithm. So what's the motivation for this? So in practice, we'll find that we will not only interested in computing the marginal distribution of, say, a bunch of variables in your graphic model. We're also interested to look at the configuration of all the random variables in your graphic model, which maximize the joint probability. Why is this useful? Right? There's a large machine learning task called structure prediction. Right? For example, if you want to do some semantic parsing, right? You want to post positive speech tagging, right? And you actually model the whole sentences or graph as a graphic model, right? Each node may correspond to the post tag for a word or sentiment preferences for a word or phrase or those kind of stuff, right? And of course, the post tag of different words are related to each other, right? So once you build up a graphic model to model their joint probability, and you train that, when you give a new sentence, of course you want to infer a sequence or set of post tags to maximize the joint probability. You believe that is the correct post tag. So this is very useful in many structure prediction problems, as long as you're trying to jointly predict a bunch of labels rather than just one label. Right? Then that comes a problem, right? How do you efficiently find out this setting? Right? So someone may ask, right? Now that we got powerful tool to compute the marginals, right? Why not just use message passing over the sum product algorithm? We can retrieve the marginal for every variable, right? And then according to the marginals, I pick up the maximum value, Argmax of each marginal. Okay. However, in general, the maximum marginals usually is not joint marginal. Okay. So how can we see this? Right? If you look at this table, right? X and Y, right? X can take two possible values, Y can take two possible values, right? And what is the XY pair that maximize the joint probability? Anyone can tell me? I heard that here, right? So that means the joint maximum is achieved when x equals to 1 and y equals to 0, right? So that means, okay, if we want to look at what's the particular choice of x that leads to the maximum joint probability, x should be 1, right? However, if you look at the marginal distribution of x, right? If you look at marginal distribution of x, you will see that the probability of x equal to 0 is 0.6, and for x equals to 1 is 0.4, right? So now we see that the x value that maximizes the marginal probability, which is simply 0. So now you can see the inconsistency, right? So you maximize the marginal probability is not equal to you maximize the joint probability. Right? And in practice, we actually want the configuration of all the random variables that jointly maximize the joint probability. Does it make sense? Right. So how can we do that? How can we do that, right? Again, we can apply the distributive law, right? You see that max coupled with product also satisfy the distributive law. Right? Again, we use this chain graphic model, right? So we want to find out the variable values which maximize the joint probability. That means we're going to maximize with respect to x1 to xm over this joint probability, right? This joint probability can be written as the product of the factors over this, here is potential functions. Okay? And you can see that you can still apply the max first over the potential function and then multiply with the preceding potentials, right? Does it make sense? Okay. So that gives us a possibility, right? Can we just apply the sum product algorithm framework by like slightly modify the framework? We can do this efficiently. So the answer is yes, right? So first, we observe that we have this distributive law, right? When we maximize the product, two products, right? A, B, and AC, it is equivalent to first maximize the common factors B and C and multiplying with A, right? So here we use the special condition that all the factors here are positive, right? Or at least not negative. That's why we can apply that, right? That's why we can apply in probabilistic graphic models, not apply to, not mean that this does not mean you can apply to everywhere, right? This is because all the factors we're considering here are positive. So when we couple the product and the max, we can still do the distributive law, right? So you can see that our previous computation, like sum product, like sum product algorithm, it is essentially, I mean, this whole message passing algorithm, whole message passing protocols, right, are essentially a recursive application of the distributive law over the coupling of the sum and the product operations. But here we can see that when you do the coupling of max and product operations, the distributive law are still there, right? So essentially, you can apply exactly the same procedure to apply distributive law and to save the computation, right? So there's only one change, that is, I'm gonna replace my sum operation by max operation. The remaining is the same. Does it make sense? Right. And that's it. That's the max for the algorithm. And when you do the implementation, what you need to do is that, okay, I'm gonna overload this sum operation. I can write another version of my sum, which is actually doing maximize operation. And that's it. You can reuse all your sum product implementation. Does it make sense? That's very convenient. That's very easy and convenient, right? So but here, there is still a problem, the issue that if we do the max and product operation, sorry, you can imagine we're multiplying a bunch of factors, right? So, as we mentioned, you multiply a bunch of, if it is a set of probability factors, we'll multiply all together. It is easy to get on the floor, right? So, how do we improve the numerical stability, right? We want to take a logarithm, right? And it doesn't change the maximization result, right? Because we want to do the argmax, right? So if we take a logarithm over the joint probability, then do the maximization, it won't change the result. So then we can first conduct the logarithm and do the maximization. Then you can see that the log probability will convert the product of factors into the summation over the factor, right? Then the definition, then the computation becomes a coupling of max and sum operations. Does it make sense? Right? So previously we want to maximize. Sorry, it's here. Oops. Let me write down here. Previously we want to max a bunch of want to maximize the product of a set of factors, right? Right now we maximize the logarithm of product. Essentially, we want to maximize a summation of log factors, right? So now it becomes max sum operation. The question is that, can we still leverage the previous framework? The key is that we need to look at when we couple max and sum operation, if the distributive law still holds, right? And fortunately, if you do max and sum, the distributive law is still there. Now, to make a more numerical stable version, right, we just need to overload two operations, right? So previously, our original is this sum product algorithm, right? So now we just need to overload sum operator and product operator. In my new version of sum, I'm doing max. And in my new version of product, I'm doing sum. And then I get my max sum algorithm. And the whole procedure is the same. Right? The only difference is how do you conduct the details about sum and product, right? And in our case, it becomes max and sum. Right? Does it make sense? Okay. Yeah, let's stop here today. Right. On Thursday, we're going to wrap up our graphing models and talk about and start talking about approximate inference. See you on Thursday.